You know that little blue dot on your phone's map? You've probably stared at it a million times. I mean, we use it every single day, right? To find a coffee shop, navigate a road trip, make sure our takeout gets delivered. But have you ever actually wondered how it knows exactly where you are? Well, underneath that simple glowing blue circle is a staggering symphony of orbital mechanics, quantum physics, and just perfectly timed radio waves. Welcome to this explainer. Today, we're going to decode the invisible infrastructure that literally guides modern human life. Let's get into it. Here is the flight plan for this explainer. We'll be hitting Section 1, Constellation and Signal Structure, Section 2, Trilateration and Intersecting Spheres, Section 3, The Fourth Satellite Secret, Section 4, Einstein's Relativity in GPS, and finally, Section 5, the Ground Control Segment. Think of this like a system boot sequence, taking us all the way from massive space infrastructure down to the mind-bending quantum physics on your screen.
Section 1, Constellation and Signal Structure, the Space Infrastructure. Okay, let's kick things off with the macro view, way up above our heads. To make this all work, we rely on a massive constellation of 24 to 31 active satellites. And they aren't just hovering in one spot either. They're up in medium Earth orbit, exactly 20,200 kilometers above us, zooming around the planet and completing a full orbit every 12 hours. Because their orbits are tilted at this specific 55-degree angle to the equator, your phone almost always has a direct, clear line of sight to at least 4 of them, pretty much anywhere on Earth.
So what are they actually doing up there? Basically, they are incredibly precise, incredibly loud clocks. They're continuously broadcasting 2 key pieces of information: their exact position in space and the exact time they sent the signal. They do this using unique pseudorandom noise, or PRN codes, embedded right into a carrier signal. And these radio waves travel down to us through the vacuum of space at the speed of light, which is exactly 299,792,458 meters per second.
Section 2. Trilateration and Intersecting Spheres, Visualizing the Math. Now, let's see how that space data comes down to your device to build the mathematical foundation of your physical location.
You've probably heard the term triangulation thrown around in spy movies, but GPS actually uses something called trilateration. Instead of measuring angles, it measures pure distance. It relies on a formula you probably remember from grade school. Distance equals rate times time. The rate is the speed of light. The time is the exact amount of time it took for the satellite's signal to hit your receiver. You multiply those together and boom, your phone knows exactly how far away that satellite is. This visual perfectly illustrates the math. Imagine you know your distance from just one satellite. That means you could be anywhere on the surface of a giant invisible sphere centered around it. Calculate your distance from a second satellite and you get a second sphere. Where those two intersect makes a circle. Now add a third satellite, and its sphere intersects that circle at just 2 specific points. And since one of those points is usually out in deep space or buried underground, well, you know you have to be at the other one. 3 distances, 3 spheres, 1 exact location.
Section 3, The Fourth Satellite Secret, Solving the Time Flaw. But hold on a second. There's actually a massive flaw in this 3-sphere detective story. Here's the catch. That whole trilateration math formula entirely relies on knowing the exact time the signal took to travel. And remember, we're talking about signals moving at the speed of light. So if your phone's clock is off by even a tiny fraction of a single second, your calculated distance is going to be wrong by hundreds, maybe thousands of miles. And let's be real, your smartphone definitely doesn't have a multi-million-dollar perfectly synchronized atomic clock inside it. So how does this cheap clock not just ruin the whole thing? Enter the fourth satellite. It's a total game changer. In algebra, if you have 4 unknown variables, in our case, your x, y, and z coordinates, plus your clock's time error, you need 4 equations to solve for them. By pulling in a signal from a 4th satellite, your phone's software gets that 4th equation. It can elegantly solve the math to instantly figure out its own clock offset. It mathematically corrects your phone's time to match those atomic clocks in space, fixing the distance calculation perfectly. It is honestly a genius workaround.
Section 4. Einstein's Relativity in GPS, Bending Time. So, we've got perfectly synchronized clocks, right? Well, now we hit the ultimate boss level of physics. We literally have to bend time.
I'm not exaggerating when I say that without Albert Einstein, your navigation app would be totally useless. Every time you order a pizza and watch that little car icon turn down your street, you are actively relying on the theories of special and general relativity.
It's kind of like a cosmic tug of war between 2 relativistic effects. First, you have special relativity. Because the satellites are moving incredibly fast compared to us down on Earth, about 3,870 meters per second, their clocks actually tick slower. But then we have general relativity to deal with. Because those satellites are 20,200 kilometers away from the center of Earth's mass, they feel much weaker gravity. And according to Einstein, less gravity means time moves faster.
Let's look at how the math actually shakes out. Special relativity causes the satellite clocks to lose 7,210 nanoseconds a day, but general relativity causes them to gain 45,850 nanoseconds a day. When you look at the net difference, the GPS satellite clocks are actually running faster than our clocks on Earth by about 38,640 nanoseconds every single day. To account for this, engineers literally have to build the satellite clocks to tick slightly slower on the ground, at 10.22999999543 MHz instead of a flat 10.23, so that once they reach orbit, the time-bending effects of the universe speed them up to be perfectly in sync with us. How wild is that?
Now, you might be thinking 38,640 nanoseconds, that's microscopic, who cares? Well, remember, we are multiplying that time by the speed of light. If engineers didn't actively account for Einstein's time-bending physics, those nanoseconds would compound fast. Your GPS location would drift by a massive 11.7 kilometers, that's over 7 miles, every single day. Within a week, your phone would confidently tell you you were in a completely different city.
And while Einstein perfected the math, this concept actually traces its roots all the way back to Galileo Galilei. He was an early pioneer of the relativity principle centuries ago, pointing out that the laws of physics are exactly the same in any system moving at a constant speed. It really shows how centuries of incredible physics and astronomy are just seamlessly converging right there in your pocket.
Section 5, the ground control segment, the human element. Let's bring this explainer back down to Earth for a minute. Space math is fantastic, but who's actually keeping the lights on?
A system this complex doesn't just run itself. It requires a massive amount of human oversight, known as the control segment. Operating through 11 command antennas and 17 monitoring sites scattered all over the globe, the master control station does the heavy lifting here. They use radar to constantly track the satellites to ensure they are exactly where they're supposed to be. If an orbit degrades even slightly, or a clock drifts, the ground crew generates navigation messages and uploads incredibly precise corrections back to the satellites to keep the whole constellation healthy.
And who exactly is running this sleek, high-tech operation? It's a crew nicknamed Team Blackjack. We're talking about the dedicated men and women of the U.S. Space Force's 2nd Navigation Warfare Squadron and the Air Force Reserve's 19th Space Operations Squadron out in Colorado. They are at the consoles 24/7, resolving anomalies and maintaining this pristine accuracy for literally billions of users around the world. What absolutely blows my mind is this realization. Every single time you open an app for directions or just tag a photo with your location, you are holding a device that actively, repeatedly confirms the most fundamental, mind-bending laws of our universe. It is literal everyday magic, made possible by just brilliant engineering.
So I'll leave you with this thought. It's never just a map. It's a masterpiece of orbital mechanics, atomic precision, and relativity all working perfectly together to guide you home. The next time you look down at that glowing blue dot on your screen, will you just see your location, or will you see the incredible cosmic infrastructure and quantum physics that actually put it there?